Okay, let's begin the review of the intermolecular forces. Like I said, it's very, very important for whole understanding of chemistry. Okay, I know you already know some stuff, but then the way I ask you a question and you're not answering right away, there is something needs to be reviewed. Okay, so it's good timing. So we talk about intramolecular bond versus intermolecular bond, right? Okay. All right. Remember how intra was what? Between
Um,
atom to atom.
yeah.
Uh-huh. And the inter was what? Between molecule to molecule. Hmm. So we talked about three biggest bonds, right? All the intermolecular forces. The first one was what? Ionic. We talked about covalent. And we talked about metallic, right? Where ionic bond is where between two atoms that has one electron was given off to the other, and usually this is a metal, and this is the non-metal, and given away electron becomes one side becoming positively charged, the other side becoming negatively charged. Because the opposite charges, they attract each other to form a bond. Okay? That's what ionic bond is basically, right? They form an ion, they bond. Pretty simple, right? One of the examples they use is what? Sodium with a chlorine, where sodium gives off that one electron, right? And then making sodium ion and chlorine ion come together as NaCl, the one salt compound. Okay, that's one of the strongest bond between element to element. Okay, one part that you can also distinguish by numerically is when it comes to electronegativity. Electronegativity is greater than 1.7. We consider that as a ionic bond. Generally, most of a metal to nonmetal will give you that value when you look at the chart of electronegativity chart. Okay. Covalent bond is slightly a little different, where well, first I guess we can say the electronegativity is going to be greater than greater than no, it's less, has to be less than 1.7, of course, as electronegativity, but greater than 0.4. Okay. So that means the difference of electronegativity compared to ionic covalent is quite weaker. The covalent bond actually has two categories. One is polar covalent, and there's nonpolar. Where nonpolar covalent, so this is going to be the value for polar covalent, and for nonpolar, anything less than electronegativity is less than 0.4 is going to be nonpolar covalent. So what does that mean? Anything that has a polarity, let's just look at the example of what I always draw. Let's say we have a B, C, N, O, F on a periodic table. Okay, so remember that fluorine is a high electronegative. These are the weaker ones, and going from high to low. Okay, that direction. So high to low. High to low is electronegativity. Okay, so what if we have a carbon monoxide? We also give you a lot of example of this, right? They are a high electronegativity, but electronegativities are close to each other, sitting somewhere between these two values. So when it comes to carbon and oxygen between two, well, number one, they are usually what? Well, I mean, they're not usually, but they are what? Non-polar compounds. Well, not non-polar compound, but non-metal compound, should I say? Actually, it's a non-metal compound. So they don't really do that, all the exchange of electrons given one from the other side, right? So they don't really form. However, because electronegativity, oxygen is greater, than carbon is, when they form a bond, they form a unequal inequality, meaning that oxygen withdraws electron greater to from away from carbon. So if I have to exaggerate that orbital, this side, oxygen side, has a high electronegativity, withdrawing electrons toward more to the oxygen compared to carbon is. Okay? This creates partial negative charge and then partial positive charge to it. So this creates this polarity. That's why called polar covalent bond. So generally electrons are shared unequally. Okay, so being oxygen side, greater concentration of electron than carbon is because electronegativity is greater. Okay. Now then, okay, non-polarity means what? The electronegativities are quite close to each other. So let's just use a oxygen molecule, which is O2. So that means what? Between oxygen to oxygen, the electronegativity is exactly the same. So when there's a bond formation occurs, what happens is what? The electrons are equally shared between two. Okay, almost equally shared between two. So there's no polarity. Okay, so you can't see the polarity, right? So that's what the covalent bond is. For the metallic bond, of course, metallic bond is basically what? Between metal to metal. Going back to here, this will be what? Non-metal to non-metal, basically. Okay, general stance. This was a metal to the metal, right? So metal to metal, we talked about that here last time, where we have some kind of metal compound, and these are all, let's just say it's copper atoms, okay? And electrons are what? Moving freely. Let me put a different color. Moving freely, from neighbors to neighbors. Now once this part of the electron is emptied out, not emptied out, well, when the electron is moved away, the neighboring of the electron kind of fills that in. So it has a random movement of electrons happening. We call this what? Sea of electrons. Okay. Until when? Until when we have a battery that's connected to this copper wire. Then remember that the flat side is negative charge, and this when you have a little nipple on it is a positive side. That causes basically you have this electron, random movement electrons now will be attracted to that positive terminal, and then it will be sucked into that positive terminal. So this electron that was here floating around is now gone. What happens is this negative side is going to replenish all the electron that was missing to the positive terminal. So it creates a circuit. Okay. So because these electrons are moving kind of freely even before it was connected to a battery, it kind of has this free movement, and that kind of gives you that metal characteristic of what? You can easily bend it. Once you bend, it kind of stays there. So it kind of gives some flexibility to it. That's what the characteristics of the metallic bond would be like. Okay. So these are the intramolecular forces in general. Okay. Now our important part also go into is what? Intermolecular forces. Okay. So let's kind of go into the intermolecular forces. So one of the stronger, there are stronger forces out there, but in general, hydrogen bond is one of the strongest. Okay. Remember that the requirement of the hydrogen bond was what? It requires F-O-N, FON, right? So let's take a look at that as an example. So we have water molecule here, and I'm going to create a hydrofluoric acid here. Okay. And you already know oxygen, looking at this chart of a periodic table, and usually hydrogen sits right here, once again. Hydrogen right between boron and carbon when it comes to electronegativity strength-wise. So you can tell oxygen is much higher electronegativity than the hydrogen is. Therefore, you will have this unequally shared electron density to the oxygen, creating partial negative here, partial positive here. So The whole interstructure has a permanent positive side and permanent negative side. Same thing to the hydrofluoric acid. Fluorine is one of the highest electronegativity. Of course, we will have that same thing. Doing that as a high intensity of electron here, creating partial negative, partial positive. So when they are next to each other, because of the partial positive and partial negative here, they'll attract. Okay, so this is a hydrogen bond. Okay, let's take a look at nitrogen example too. Okay, so we have nitrogen with this. So generally this is going to be ammonia, right? So we have a high electronegativity toward the nitrogen. Maybe I should draw that lone page. And creating what? This high density of electrons toward nitrogen, creating partial negative here, partial positive here. And that creates what? The attraction forces between the positive and negative, right there too. And even for this one too, here's a positive, here's a negative, right? They form that bond there too. So all these are hydrogen bond. So what does a hydrogen bond require once again? Requires a 3 highest electronegativity atoms out of all, which is FON, that's what this is, right? And then it has to connect with a hydrogen to it, and neighbor of that hydrogen also has to be part of FON. Okay? So this FON is directly connected to the oxygen or fluorine or nitrogen, here, here, here. And of that hydrogen also has to be neighboring with one of the FONs. Okay? That's where the hydrogen bond forms. So, you're going to ask me, now, how about when we have, let me actually draw with a different color. We have this now. Okay. We have a methane. Okay, so if you look at methane, you have a carbon here, hydrogen here. They are very close to each other when it comes to electronegativity, but there are some still polarity there, but not as great as others are. So it creates this little electron density toward the carbon from all the hydrogen around it. So they will create this little negative toward the center of the carbon-wise, and then oxide partially positive. And yes, because it's positive here, negative here, they will form the bond too. But by the definition of a hydrogen bond we talked about earlier, this hydrogen is neighboring with oxygen, but it's not connected with one of the FONs. So this cannot be called hydrogen bond. That's not hydrogen bond. So anything that is less than hydrogen bond, we call it dipole. Dipole. Like I said, some textbooks say dipole, some textbooks say dipole moment, dipole interaction, doesn't really matter. Okay, as long as dipole is in there. Okay? So that means anything that is not categorized into this is considered a dipole. Okay. So another good example you can think about is what? Basically, we talked about this carbon monoxide earlier. So if you have a carbon monoxide having partially negative here, partially positive here, and you have another carbon monoxide, partially negative, partially positive, partially negative, and there'll be interaction between two. And it has nothing to do with any hydrogen bond at all. So this interaction will be what, basically? Dipole. Okay. Number 3, LDF. So what is LDF then? Okay. So LDF is when, we also given an example of what? Dippin' Dots, the ice cream shops, making how they create those ice creams, right? Using liquid nitrogens. Okay. Well, if you look at the nitrogen structure, as we also seen before, okay. If you look at here, nitrogen to nitrogen, they have what? Exactly the same electronegativity. Therefore, what's happening here? It's going to be what? Equally shared electrons, almost equally, right? So when you have another nitrogen next to it as a molecule, and it goes shared, they won't have a chance of actually what? Coming together and to make a bond. It's not going to be easy. That's why N2 is a gas state in room temperature, or even lower. Okay. So what do we need to do to make the bond together? Okay. Remember we talked about what? Kinetic energy is equal to what? Proportional to temperature. Therefore, if you were to decrease the temperature, kinetic energy will decrease. So that means the speeding of electron between two nitrogens here and also here will start to slow down. So when that slowdown occurs and electrons are positioning at this point, then it will create a temporary partially negative charge there and partial positive charge there. Would that stay permanently? No. The electron will go right back and making this side negative now, and that side positive. It's just a slower motion because temperature is decreased and kinetic energy at the same time is decreased. What's that happen to this too? So when there's a right moment, when in lower enough temperature, where partial negative, partial positive here, and then sweeping back again and partial positive, partial negative here, and whenever they are meeting this opposite side, that's when they are forming a bond to each other. And I believe, I will double check that temperature once again, I think it was a negative 190 degrees Celsius as a freezing point. Or, so nitrogen, condensation. Condensation point. So it's a negative, 190 degrees Celsius. Okay. So when it reaches negative 190, to be more exact, 95 degrees Celsius, then these start to form, and then the gas state of nitrogen will start to become liquid nitrogen. Okay. So, because the movement is slower as the temperature goes down. Okay. So, is this bond stable? Of course, at this, as long as you keep the temperature low enough, it will be stable. But this bond will actually keep flipping back and forth. What does that mean? Once this is happening, it will form between two where the electrons are off this side and electrons are this side now. Okay. And remember that the electron will flip back, and so is this electron flip back too. So forming another bond between them two. Okay. So this is going to be going back and forth. This electron keep on as much as these electrons are keep on going back and forth, and this one is doing the synchronized movement somehow. Then, more likely by chance, then they will form the bond which is called LDF, London Dispersion Force. Okay, and we also talked about what? We compare this to how strong this bond might be. And we talked about EriCo, right? Also geckos. How do geckos, or even frogs, do they get to stick on the wall or glass, even upside down? Is it because the surface of their paw, probably a little more circular than the tip, and this surface has a lot of fibers at the end, if you look at microscopic way, that gives a lot of, like, millions and billions of connections to the outer surface with LDF. So that enough number of forces with the LDF creates enough stickiness for them to sustain sticking on the wall or even sitting. Okay? So, like I said, this is, like, once again, based on every single intermolecular force contents out there, and you cannot forget this, especially when you, as we are entering the second semester portion, and you already see when we are talking about viscosity and vapor pressure and all has to do with these intermolecular forces. And remember that how ethanol versus water, why was water less volatile compared to ethanol was. Remember, ethanol had a dipole, even though it was dipole too, but then they had a hydrogen bond, but the less number of hydrogen bond compared to water has a whole lot more hydrogen bond around it, right? So that creates huge difference of volatility of a molecule, okay? So you gotta nail this. You cannot forget this. So whenever I ask, these three things have to pop out of your mouth right away. From now on, okay? You cannot forget these things, okay? Do we have all the things cleared in this section?